Welcome back to another video on the equations of statistical mechanics. This is our 6th video on statistical mechanics, and after this video we're probably going to take a break and jump into quantum mechanics, which is some pretty scary stuff. However, at this point we've essentially exhausted all of the interesting things that we can do without introducing quantum mechanics. We'll come back to statistical mechanics again, but this should be our last video for some time. Recall in our last video that we derived the partition function and Boltzmann's distribution, which informs us of the probability that a certain state is occupied. And we finished off our discussion by talking about two-level systems and what we can learn about energy states. Now, while this was nice, we only spoke about a finite number of systems, in particular 2. This works well in some situations, once again think quantum mechanics, but for the most part these videos have dealt with statistical mechanics where we have an almost countless number of particles, and often the number of energy states are even larger, think boxes of gas. Thus, we need to think about our partition function in a different way. Before we get there, I'd like to derive 4 more equations that relate thermodynamic variables to the partition function. The thermodynamic variables are entropy, energy, pressure, and the Helmholtz free energy. There are several more thermodynamic variables that we could derive, such as the chemical potential, and we could also look at different ensembles, such as the grand canonical ensemble, or the isothermal isobaric ensemble, but I think sticking with the canonical ensemble is the simplest and potentially most intuitive. However, one thing that you have to remember is that in this ensemble we have a fixed temperature, volume, and number of particles. If the system you're working with has fixed pressure, for example, you need to move to the isothermal isobaric ensemble with Gibbs free energy instead of Helmholtz free energy, but that's not that difficult. To motivate the derivation of the partition function and the Boltzmann distribution, we started with the Gibbs entropy equation, which states that the entropy is equal to minus the negative Boltzmann constant multiplied by the summation of the probability of a state multiplied by the natural log of that state over all states. Now, we use our Boltzmann distribution for the probability, and if we plug this into our equation, we could figure out what the entropy is. The Boltzmann distribution states that the probability of an individual state is equal to the natural number E raised to the negative energy of that state divided by the Boltzmann constant multiplied by temperature all over Q, the partition function. As a reminder, the partition function is the sum of the natural number E raised to the negative energy of a state divided by the Boltzmann constant multiplied by temperature over all states. When we plug the Boltzmann distribution into the Gibbs entropy equation, we first want to use our properties of logarithms to separate this into 2 terms. The natural log of the natural number e raised to an exponent simply returns the exponent here. At this point, I'm going to break the equation into 2 sums and move our q's in the denominator outside of the sum. In the second term, we see that the summation is just the partition function, so we simplify this to q, and then we cancel the q's in the numerator and the denominator. However, this first term is going to be more difficult and we'll have to be a bit sneaky to get this into a nice form. This trick is going to be utilized in all these derivations, so I'm going to go over it here in some detail. Suppose we take the derivative with respect to temperature of the natural number E raised to the negative energy of some state divided by the Boltzmann constant times temperature. When you take the derivative of the natural number raised to some expression, the derivative is equal to the natural number raised to that expression multiplied by the derivative of the expression. The energy is not a function of temperature. Its natural variables are entropy, volume, and number of particles. So when we take the derivative, we treat it as a constant, and if we rearrange the expression in the exponent, we see that we have some constants multiplied by temperature raised to the negative 1. When you take a derivative of an exponent, you bring the original exponent down, subtract 1 from the exponent, and multiply by the derivative of the base. The derivative of temperature with respect to temperature is 1, so the derivative of this function is just the negative energy of a state divided by Boltzmann's constant, all times the negative temperature raised to the negative 2, or we can rewrite this as the energy of a state divided by Boltzmann's constant times the square of temperature. As a side note, I'm not going to be explaining all the rules of derivatives that we're going to use here, but you can check out a course into introductory calculus if you want to see these derivations in depth. However, the derivative of this term is equal to the energy of that state divided by the Boltzmann constant times temperature squared, all multiplied by the original function, the natural number E raised to the negative energy of a state divided by the Boltzmann constant times temperature. With this equation in mind, We return to our original equation and we see that we almost have this expression if only we had an extra temperature. Fortunately for us, we can always multiply any term by 1, but we're going to do it in a strange way, by multiplying by temperature divided by temperature. We then move one temperature into the sum because it's a constant, and we now have the expression we're looking for. We substitute this in for the expression with the derivative, and because derivation is a linear operator, we move it outside of the sum. Basically what this means is that if we had a sum over multiple terms and we took the derivative of the sum, it would be the same thing as taking the derivative of each term and then summing them together. By doing this, our summation takes the familiar form of the partition function, and the entropy is thus equal to Boltzmann's constant times temperature divided by the partition function multiplied by the derivative of the partition function with respect to temperature plus Boltzmann's constant times the natural log of the partition function. We are going to do one more simplification of this equation. The derivative of the natural log of x with respect to y is equal to 1 over x multiplied by the derivative of x with respect to y. Thus, the first term can be simplified to Boltzmann's constant multiplied by temperature multiplied by the partial derivative of the natural log of the partition function with respect to temperature, giving us our final expression for the entropy, and now we have a very nice equation to work with. As I said, moving forward with quantum mechanics, we'll be able to get expressions for the partition function that we can take the natural log and the derivative of. One thing to mention about this equation, if you recall our video on the derivation of the Gibbs entropy equation, is that this gives us an average entropy. However, for doing thermodynamics, this is completely fine. In our first video on entropy, we discussed how increasing the number of coin flips that we did narrowed the probability distribution of the proportion of coins that would return heads. If we allowed our number of coin flips to approach infinity, this probability distribution would narrow such that the proportion of coins that are heads would always be equal to 1/2 for an individual measurement. Thus, the average value approaches the true value for an individual measurement. The same is the case when considering populations of molecules or atoms in statistical mechanics. The average observed entropy, or energy, or pressure is the observed experimental entropy, energy, or pressure, simply because we are sampling such large numbers. As we are currently in the canonical ensemble, there is no fixed energy for the ensemble. The fixed variables are temperature, volume, number of particles, and the Helmholtz free energy. However, we can still calculate an average energy, similarly to how we calculated an average entropy. When computing averages, we could just take the energy of a microstate and multiply it by the probability of that state, and then sum these all together to get the average energy. We substitute in our Boltzmann distribution for the probability, and we can then remove the partition function q from the summation. If you notice, we have a very similar expression to what we worked with before with our entropy equation. We multiply our expression by 1 in the form of Boltzmann's constant times temperature squared divided by itself, and we pull the denominator into the summation. Using our previously defined expression for the derivative of the natural number e raised to the negative energy of some state divided by Boltzmann's constant times temperature, we turn this expression into a derivative and remove the derivative from the summation. The summation is now the partition function, and we substitute q in here. Finally, we see that we have the same form of the derivative as before, and so the energy is equal to Boltzmann's constant times temperature squared multiplied by the partial derivative with respect to temperature of the natural log of the partition function. We can perform this type of manipulation one more time to calculate the pressure of such a system. We want the average pressure, so we sum over all the states with the pressure of each state multiplied by the probability of that state. Substituting in the Boltzmann distribution and removing the partition function like we have before, we see that the average pressure is equal to 1 over q multiplied by the summation of the pressure for a state multiplied by the natural number e raised to the negative energy of that state divided by the Boltzmann constant times the temperature. Fortunately, we have previously shown from the total differential of energy with the first law of thermodynamics that pressure is equal to the negative partial derivative of energy with respect to volume, and we go ahead and substitute this in here. We multiply this expression by 1 in the form of the Boltzmann constant times temperature divided by itself, and we pull the denominator inside the summation. Once again, the expression inside the summation is a derivative of the natural number e raised to the negative energy of a state divided by the Boltzmann constant times temperature, but instead of being with respect to energy, This time it is with respect to volume. Following our explanation, when we were working with derivatives with respect to temperature, we can now treat temperature as a constant. However, we cannot treat energy as a constant as one of its natural variables is volume. Thus, the derivative of this exponent is simply -1 over Boltzmann's constant times temperature times whatever the derivative of energy is with respect to volume. Thus, we see that inside our summation, we have the derivative of the natural number E raised to the negative energy of a state divided by Boltzmann's constant times temperature with respect to volume. So we substitute this in here, remove the partial derivative from the sum, and we once again have the partition function. Following the same rules as our derivations above, we see that the average pressure is equal to Boltzmann's constant times temperature multiplied by the partial derivative of the natural log of the partition function with respect to volume. In theory, we can derive all sorts of experimental measurables using this approach. The final thermodynamic variable that I want to derive is the Helmholtz free energy, and it is quite simple. We know that the Helmholtz free energy is defined as the internal energy minus the temperature times the entropy. Now we have these expressions for energy and entropy, we can substitute these in. We see that the first two terms in this expression actually cancel out, and we are left with the Helmholtz free energy being equal to the Boltzmann constant multiplied by temperature multiplied by the natural log of the partition function. At this point, we've taken statistical mechanics basically as far as we can without introducing quantum mechanics. If we knew what the energies of these states were, like the energy states of particles of a gas inside a box, we could use that in our partition function and take derivatives to calculate measurable thermodynamic variables. This is going to be a long ways off. We have a lot of quantum mechanics to do, but eventually we can use the expression we've derived here for pressure to derive the ideal gas law, one of the first laws of physical chemistry introduced to students, and in my opinion one of the most satisfying results of statistical mechanics and simply thinking of large collections of molecules. Thank you for watching this video on the derivation of the thermodynamic variables from the partition function. If you enjoyed this video, please like and share this video as it helps considerably in increasing outreach. If you want to see more videos on chemistry and physics topics, please consider subscribing to the channel. I have linked my Patreon page in the description below, and if you would like to support educational content like this, please consider donating. Finally, please comment below if there's something you feel like I could make more clear, or if there are other topics that you would like me to cover. Thank you.